Hello friends, good afternoon and welcome to Reset Live Lectures. Dear friends, as you know that we started a series on natural products and spectroscopy, and today we are conducting yet another lecture in the same series. In today's lecture we will be continuing with IR Spectroscopy, and this will be part 2 of IR Spectroscopy. To discuss this topic we have with us our subject expert Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you so much. Hello viewers, in the series of natural products and IR spectroscopy, in the last lecture I have discussed about the IR spectroscopy, which kind of compound will give you IR spectra. And we have also talked about that in IR spectroscopy specifically, we are discussing about the function group. With the IR spectroscopy, we can analyze which kind of functional group is present in given organic compound, and what are the organic compounds which gives IR spectrum, which are IR active compounds. So, we have discussed this IR spectroscopy fundamentals, that we need to follow the IR rays on compounds, and there is a transition of energy, that is delta is equal to h nu, and transition involved IR absorption with vibrational changes within the molecule. We have discussed in the last lecture about the instrumentation part also, and about some alkane and alkyne. Today I will go through in depth about the CH stretching region, whether we are talking about alkane or alkene or aldehydes or carbonyl compounds or ethers. So, what are the depth in CH stretching region? The CH stretching and bending regions are of two most of difficult region to interpret in IR spectra. The CH stretching region, which ranges from 330 to 2750 centimeter inverse, is generally the more useful of the two. The frequency of absorption CH bonds is a function mostly of types of hybridization, that which kind of hybridization is there in the molecule. For example, the sp2-1s, that is CH bond present in acetylenic compound, is stronger than sp2-1s bond present in carbon double bond carbon, or we can say in vinyl compounds. This strength results in larger vibrational force constant and a higher frequency of vibration. Likewise, the sp2-1s in CH absorption in vinyl compounds will occur at higher frequency that in saturated aliphatic compounds for the same kind of hybridization. The frequency at which CH absorption occurs indicates the type of carbon to which hydrogen is attached. Except for the aldehydic hydrogen, an absorption frequency of less than 3000 usually implies a saturated compound. An absorption frequency higher than 3000 but not above about 3150 usually implies aromatic or vinylic hydrogens. However, cyclopropyl carbon hydrogen bonds, which have extra 5 character because of the need to put more p character into the ring carbon-carbon bonds to reduce angle distortion, also give rise to absorption in the region of 3100 value. You can see the table here, the type of bonds are given, and you can see this is sp1s because this triple bond is there, sp2-1s double bond C carbon and hydrogen, sp3-1s, that is carbon hydrogen. So, you can see the comparative study, there are lengths 1.08 for acetylenic, and you can see this is 1.10 for sp2, 1.12 for sp3. You can see the strength of the bond, and here you can differentiate also with the help of IR spectrum, that for this sp1s the value is 3300, and consequently as the hybridization goes from sp to sp3, the value decreases. So, here you can see for sp2-1s this is 3100 and for sp3 it is 2900. So, from the spectrum you can easily differentiate that which type of carbon hydrogen bond among these three are there. Here again you can see comparative study. This is acetylenic. These values are for vinylenic, aromatic and cyclopropyl. This is for aliphatic and this is for aldehydic. Here you can see strain moves absorption to left and increasing S character moves absorption to left. So, these are the CH stretching region for different kind of carbon hydrogen bond. The aldehyde carbon hydrogen stretching frequencies appears at lower value than saturated carbon hydrogen absorption and normally consist of two peaks at about 2850 and 2750. They should present all together when you need to analyze this carbon hydrogen aldehydic functional group. The 2850 band usually appears as shoulder on the saturated carbon hydrogen absorption bonds. The band at 2750 is a rather weak bond and may be missed in an examination of the spectrum. However, it appears at lower frequency than aliphatic sp3 carbon hydrogen bonds. If you are attempting to identify an aldehyde, look for this pair of weak but very diagnostic band for the aldehydic carbon hydrogen stretching. So, you can analyze aldehydic carbon hydrogen with these values as well as the main values of aldehydic group. The tertiary carbon hydrogen or we can say methine hydrogen gives only one peak for CH stretching absorption. Where will it occur? It will occur at 2890. So, we need to learn these values to identify the particular kind of carbon hydrogen stretching vibrations. Methylene hydrogens or we can say CH2 however give rise to two carbon hydrogen stretching bands representing the asymmetric, we can represent like SYM and asymmetric representing by ASYM. So, both the stretching vibration should be there, asymmetric as well as symmetric. In effect 2890 methine absorption is split into two bands. One is 2926 for asymmetric vibrations, 2853 for symmetric vibrations frequencies. The asymmetric mode generates a large dipole moment. We know IR spectrum, which kind of compound will give you IR spectrum? Those having a significant dipole moment. Until unless a compound is having dipole moment, it cannot give a IR spectrum, or we can say these compounds are IR inactive. These are inert towards IR spectrum and is of great intensity than the symmetric mode. The splitting of 2890 methine absorption is larger in case of methyl group. Peak appears at about 2962 and 2872 approximately. Here you can say these are the methyl group and these are the stretching vibrations, asymmetric and symmetric. For methyl group it will appear at 2962 and symmetric 2872. This is for methylene values and these are for methine values. Since several bands may appear in carbon hydrogen stretching regions, it is probably a good idea to decide only whether the absorption are acetylenic, that is triple bond are there, vinylenic or aromatic, aliphatic or aldehydic. So, we have to look importantly for these kind of functional group first to have an interpretation of IR spectrum. Before, the CH bending vibrations are often more useful for determining whether methyl or methylene groups are present in a molecule. CH bending vibrations, now we are talking about the bending vibrations. The presence of methyl and methylene group when not obscured by other observations may be determined by analyzing the region 1465-1370 band due to CH2 scissoring usually occurs at 1465. One of the bending modes of CH usually absorbs strongly near 1375 value. These two bands can often be used to detect methylene and methyl groups respectively. Furthermore, the 1375 value for methyl band is usually split into two peaks of nearly equal intensity. These are for symmetric as well as for asymmetric modes. If a geminal dimethyl group is present, geminal dimethyl group is what? When two methyl groups are attached to a same carbon atom. These were termed as germinal dimethyl group. This doublet is often observed in the compounds with isopropyl group. A tertiary butyl group results in an even wider splitting of the peak into two peaks. The 1370 band is more intense than the 1390 value. In cyclic hydrocarbons which do not have attached methyl groups, 1375 band is missing, as can be seen in the spectrum of cyclohexane. Finally, a rocking band appears near 720 for long chain alkanes of 4 carbons or more carbons. Here you can see this figure can show you, these are the scissoring. You can see CH scissoring bending mode, these are asymmetric bending mode it represents, and it represents symmetric, and these are the values, approximate values. For scissoring it will be on 1465, for bending it will be 1450. Here you can see symmetric bending, it can be divided into two depending upon the group. Lone, if there is only one methyl group, it is here, and if gem dimethyl groups are there, then this peak will be divided into two. One is at 1380, another peak will be observed at 1370. If you are locating for tertiary butyl group, we have to see these kind of peaks, that is 1390 and 1370, and the two bands, remember that, should be wider split as compared to this when we need to differentiate between these. This is the gem dimethyl. You can see the structure, the both methyl group, or we can say both the alkyl group, are attached to the same carbon atom. Here you can see the peak. This is CH bending pattern for isopropyl. This is isopropyl group and this is tertiary butyl group. So here you can see the wider. Here also these are splitting. Here also splitting takes place, but in a wider mode. Carbon double bond carbon stretching vibrations. Stretching carbon-carbon frequently usually appears between 1670 and 1640 for simple non-cyclic, or we can say acyclic alkenes. Carbon double bond carbon frequencies increase as the alkyl group added to it increases. Simple monosubstituted alkenes yields value near 1640. 1,1-disubstituted alkene absorbs at about 1650. Tri and tetra substituted alkenes absorb near 1670. Now, trans disubstituted alkene absorb at higher frequencies than disubstituted alkene. Unfortunately, carbon double bond carbon group has a rather weak intensity, certainly much weaker than a typical carbonyl group. In many cases such as tetra substituted alkenes, the double bond absorption may be so weak that it could not absorb in the spectrum. We have already stated that if group are attached arranged symmetrically, no change in dipole moment occurs during stretching, hence no IR absorption will be observed. An alkene which have less symmetry than trans alkene generally absorb more strongly than the later one. Double bond in rings, because they are often symmetric or nearly so, absorb more weakly than those not contained in rings. Terminal double bonds in monosubstituted alkenes generally have stronger absorption. So, we need to take care of these things, ki whether which kind of bond is there or which kind of groups are attached to this, and where the frequencies changes, increases or decreases while elucidating the spectrum of a compound of a given organic compound. Now, we are talking about the effects which affect the frequencies, whether stretching or bending. Conjugation, you know what is conjugation? When we are extending the double bond, carbon-carbon double bond with either a carbonyl group or another double bond provides the multiple bond with more single bond character through resonance. Here you can see this carbon double bond carbon get increased or conjugation in conjugation with this carbon double bond carbon through resonance. Here you can see the kind of resonance, that is delocalization of these pi electrons. A lower force constant value K, because this double bond now becomes, here you can see two double bonds, so K value will be higher side. Now you can see because of this delocalization of electrons, here you can see only one double bond, so K will be lower, thus a lower frequency of vibration will be observed for conjugation effect in any organic compound. For example, the vinyl double bond in styrene gives an absorption at approximately 1630. With several double bonds, the number of carbon-carbon double bond absorptions often correspond to the number of conjugated double bonds. An example of this is found in 1,3-pentadiene, where absorption are absorbed at 1600 and 1650. In the exception to this rule, butadiene gives only one band near 1600. If the double bond is conjugated with a carbonyl group, let us say, the carbon double bond carbon absorption shifts to a lower frequency and is also intensified, the peak will be intensified by the strong dipole moment of due to carbonyl group. Often too closely spaced carbon double bond carbon absorption peaks are observed for these conjugated systems, resulting from two possible conformations. Another effect which affects the frequencies, the IR frequencies, are ring size with internal double bonds. The absorption frequency of internal, can be endo double bonds in cyclic compound, is very sensitive to ring size. The absorption frequency decreases as the internal angle decreases of the ring until it reaches a minimum of 90 degree, for example in cyclobutene. The frequency increases again for cyclopropane when the angle drops to 60 degree. This initially unexpected increase in frequency occurs because the carbon double bond carbon vibrations, stretching vibrations in cyclopropane is strongly coupled to attached carbon double bond carbon single bond vibrations. When the attached carbon single bond carbon bonds are perpendicular to the carbon double bond carbon axis, as in cyclobutene, their vibrational mode is orthogonal, that is perpendicular to that of the carbon double bond carbon, and does not couple. When the angle is greater than 90 degree, let us say it is 120, the carbon single bond carbon stretching vibrations can be resolved into two components, one of which is coincident with the direction of carbon-carbon stretching. Since component is in a line with carbon double bond carbon stretching vector, single bond and double bond are coupled now and leading to a higher frequency of absorptions. A similar pattern exists for cyclopropane, which has an angle of less than 90 degree. Here you can see the values for different cyclo compound. Here you can see this is 7 membered, so value will be 1650, and this is 6 membered, 5 membered, 4 membered, 3 membered, endo double bonds, and you can see the values, different values of IR spectrum. Strain moves the peak to the right. If an endo double bond is at the ring fusion, here you can see the two rings are fused at this bond, and here you can see the double bond. The absorption moves to the right an amount equivalent to the change that would occur if one carbon were removed from the ring. Significant increases in the frequency of the absorption of a double bond containing ring are observed when one or two alkyl groups are attached directly to the double bond. The increase are most dramatic for small rings, especially for cyclopropenes. Here you can see this is cyclopropene, this is cyclobutene, and moreover you can see that here one R group is attached to here, and here two groups are attached. So you can see the values increases in a very large amount and dramatically, and here you can see one R group in cyclobutene and two group, and how the values increases from 1566 to 1675. 5 member ring, that is cyclopentene, cyclohexene, and this is the effect of alkyl substitution on carbon double bond carbon. 1656 for cyclopropene increases to about 1788, we have seen earlier, when one alkyl group is attached to the double bond, and two alkyl group increases the value about 1883. It is important here to realize that ring size must be determined before illustrating rules are applied. For example, double bonds in 1,2-dialkyl cyclopentene and 1,2-dialkyl cyclohexene absorb nearly at the same value. So, first of all you need to identify the ring size, whether it is 5 membered or 6 membered, then you need to go to for the double bond frequency. Now, ring size effect with external double bond. External, or we can say exo double bonds, gives an increase in absorption frequency with decreasing ring size. Allene is an extreme example of an exo double bond absorption. Smaller rings require the use of more p character to make the carbon-carbon bond form the requisite small rings, and this removes p character from the sigma bond of the double bond, but gives it more s character, thus strengthening the stiffening of the double bond, and the force constant K is then increased and the absorption frequency consequently increases. Here you can see this is p orbital and this is increased p character due to angle requirement, this is increased s character, and which strengthens sigma bond of the pi system. Here you can see carbon double bond carbon stretching vibrations in exocyclic system. This is 3 membered ring, value is 178044 membered ring. This is exocyclic double bond 1678. For 5 membered, this is methylene and this is 6 membered. Now, carbon hydrogen bending vibrations for alkenes compound. The CH bond in alkene can vibrate by bending both in plane and out of plane when they absorb IR radiation. The scissoring in plane vibration for terminal alkene occurs at about 1415 value. This bend appears at this value at medium to weak absorption for both monosubstituted and 1,1 disubstituted. The most valuable information for alkene is obtained from analysis of carbon hydrogen out of plane region of the spectrum, which extend 1000 to 650 centimeter inverse. These bands are frequently the strongest peak in the spectrum, and the number of absorption and their positions in spectrum can be used to indicate the substitution pattern on the double bond. Here you can say how can we represent the out of plane bending. Here this rectangle is showing the plane and this arrow is showing the bending out of plane. Monosubstituted double bond, this substitution pattern gives rise to 2 strong bands, one near 990 and other near 910 for alkyl substituted alkenes. An overtone of 910 band usually appears at 1820 and help confirm the presence of vinylene compound. 910 band is shifted to a lower frequency as low as 10810 when a group attached to the double bond can release electrons by resonance effect. This value shifts to a higher frequency as high as 960 when the group withdraws electrons by resonance. For example, carbonyl group, for example, cyanide group. The use of out of plane vibrations to confirm the monosubstituted structure is considered very reliable. The absence of these bonds almost certainly indicates that this structure feature is not present within the molecule. Now, cis and trans want to disubstituted double bonds. A cis arrangement about a double bond gives one strong band near 700, while a trans double bond absorbs nearly 970. So, you can see the difference and you can easily analyze whether it is cis double bond or trans double bond. This information can be valuable while assigning the stereochemistry about the double bond. 1,1 disubstituted double bond, a strong band near 890 is obtained for jammed dialkyl substituted double bond. When electron releasing or electron withdrawing groups are attached, this value similar to that just given for monosubstituted double bond are observed. Trisubstituted double bond, one medium intensity band at nearly 815 will obtain. For tetrasubstituted double bond, these alkenes do not give any absorption in this region because of the absence of hydrogen atom on the double bond. In addition, carbon double bond carbon stretching vibration is very weak or it can be absent at about 1650 if present. in these highly substituted systems. Here you can see the monosubstituted carbon double bond carbon. What you can observe over here, one of the hydrogen atom get replaced by one R group, that is it is monosubstituted. For cis 1 2, that is disubstituted, but you can see the position of R, these are cis in position with respect to this carbon double bond carbon or alkene. This is showing trans, when the two R groups are inclined to each other, that is these are present opposite to this carbon double bond carbon. This is 1,1 disubstituted, or we can say gem dialkyl. This is trisubstituted, this is tetrasubstituted, and here you can see the values where these values can present. Here you can see for cis this value is approximately 700, for trisubstituted it will be approximately at 800, and for 1,1 disubstituted approximately 900, and for monosubstituted approximately 1000, and the values I have dictated in earlier slide. So, these are the different bending vibrations for out of plane carbon hydrogen for substituted alkenes. Now, aromatic rings. Aromatic compounds show a number of absorption bands in the IR spectrum, many of which are not of diagnostic value. So, we should look on only on significant values. Carbon hydrogen stretching peaks for sp2 carbon appear at value greater than 3000. Since carbon hydrogen stretching bands for alkene appear in the same range, so it is difficult whether it is due to alkene or due to aromatic compound. However, carbon double bond carbon stretching bands for aromatic rings usually appear between 1600 and 150 outside the usual range, where the carbon double bond carbon appears for alkenes, that is 1650. So, these values, or we can say these stretching bands you can observe or you can distinguish because of the difference in values. Also, prominent are of out of plane bending peaks that appear in the range of 900 to 690, which along with weak overtone bends at 2000 to 667 can be used to assign the substitution on the ring. Aromatic rings, carbon hydrogen stretching for sp2 carbon hydrogen occurs at values greater than 3000. For out of plane, bending occurs at 900 to 690, and these bands can be used with the great utility to assign the ring substitution pattern. Carbon double bond carbon in ring stretching absorption often occurs in pair at 1600 or 1475 value. Overtone combination bands appear between 2000 and 1667. These weak absorptions can be used to assign the ring substitution pattern. Here you can see this is the IR spectrum of toluene, and this is the structure of toluene, benzene ring with one methyl group. Here you can see the number of peaks. This is sp2 CH stretching, this is sp3 CH stretching. This is for mono substitution. You can see these are less intense, or you can say these are not very sharp peak, but here are the peaks, weak peaks are obtained over here. This is due to aromatic carbon double bond carbon stretching, because you can see 3 carbon double bond carbon, aromatic carbon double bond carbon. For mono substitution you can see this is because of bending vibrations. Another spectrum of ortho diethyl benzene. You can see 2 ethyl group present in benzene ring in a ortho position. So, here you can see the ortho substitution, although very weak bands are there, and this is due to sp2 CH stretching, sp3 aromatic, and due to ortho substitution due to bending vibrations. CH bending vibrations in plane. We have talked about out of plane, now we are talking about in plane carbon hydrogen bending vibrations, which occur between 1300 to 1000 centimeter inverse. However, these bands are rarely useful because they overlap other strong absorption that occur in this region. Out of plane carbon hydrogen bending vibration which appear between 900 to 690 are far more useful than the vibrations in plane. These extremely intense vibrations resulting from strong coupling with adjacent hydrogen atoms can be used to assign the position of substituent on the aromatic ring. The assignment of the structure based on these out of plane bending vibrations is most reliable for alkyl, for alkoxy, for halo, amino or carbonyl substituted aromatic compounds. Aromatic nitro compounds, derivatives of aromatic carboxylic compounds and derivatives of sulfonic acid sometimes lead to unsatisfactory interpretation. So, while interpretation of IR spectrum, first of all we need to which kind of carbon hydrogen bond are present, whether it is due to alkene, alkyne or due to carbonyl group or due to any other carbon hydrogen bending or vibrations or stretching vibrations are present. We need to interpret it very carefully while detecting this IR spectrum. Hopefully, you understood this lecture. Thank you. In the last part of the IR spectroscopy, second part, we were talking about different CH bending or stretching vibrations. Now, for aromatic compounds for monosubstituted rings, this substitution pattern always gives a strong absorption near 690. If this bend is absent, no monosubstitution ring is present. So, you can easily identify it. A second strong bend usually appears near 750. The spectrum is taken in a halocarbon solvent and 690 bend may be obscured by the strong carbon halogen stretching absorption. The typical two-peak monosubstitution pattern appears in this spectrum of toluene and styrene we have seen in the last slide. In addition, the spectrum of styrene shows a pair of bands for vinyl out of plane bending modes. Ortho disubstituted rings, let us say 1,2 disubstituted, we can say one strong bond near 750 is obtained and this pattern seen in the spectrum of ortho diethyl benzene, meta disubstituted or we can say 1,3 disubstituted ring. This substitution you can easily observe by observing the value at 690 plus 1 near 780. A third band of medium intensity can also observed at 880. This pattern seen in the spectrum of meta diethyl benzene. Para disubstituted ring or let us say 1,4 disubstituted ring, one strong band appears in the region 800 to 850 and it can observe in the case of para diethyl benzene, the bands appearing in the range of 720 to 667 region actually results from carbon double bond carbon which are out of plane ring bending vibrations rather than carbon hydrogen out of plane bending vibrations. Now, combinations and overtone bands. Many weak combination and overtone absorption appear between 2000 and 1667. The relative shapes, second number of these peaks can be used to tell whether an aromatic compound is monosubstituted, di, tri, tetra or penta or hexa substituted. Positional isomers can also be distinguished since the absorption are weak. These bands are best observed by using neat liquid or concentrated solutions. If the compound has a high frequency carbonyl group, this absorption will overlap the weak overtone band so that no useful information can be obtained from the analysis. The monosubstitution pattern that appears the spectra of toluene styrene is particularly useful and helps to confirm the out of plane data we have already discussed in last slide. Likewise, the ortho and meta para disubstituted patterns may be consistent with the out of plane bending vibrations. The spectra of ortho diethyl benzene, meta diethyl benzene and para diethyl benzene each show band at both 2000 as well as to 1667 and 900 to 690 regions consistent with their structures. Note, however, that out of plane vibrations are generally more useful for diagnostic purposes. Now, for alcohols and for phenols. Alcohols and phenol will show strong broad hydrogen bonded oxygen hydrogen stretching bands centered between 3400 and 3300. In solutions, it will also be possible to absorb a free hydrogen bond, that is OH, non-hydrogen bonded stretching band at about 3600. It is sharp and weak to the left of the hydrogen bonded, that is ortho oxygen and hydrogen peak. In addition, a carbon oxygen stretching band will appear in the spectrum at 1260 to 1000 centimeter inverse. The free hydrogen oxygen hydrogen stretching is a sharp peak at about 3650 to 3600. This band appears in combination with the hydrogen bonded oxygen and hydrogen peak when the alcohol is dissolved in a solvent. The hydrogen bonded OH band is a broad peak nearly 3400 to 3300. This band is usually only one present in an alcohol that has not been dissolved in a solvent. When the alcohol is dissolved in a solvent, the free OH and the hydrogen bonded bands are present altogether with the relatively free OH on the left. Now, carbon oxygen hydrogen bending appears as a broad and weak peak at about 140 to 220, often obscured by CH3 bendings. Carbon oxygen single bond stretching vibration usually occurs in the range of 1260 to 1000. This band can usually assign a primary, secondary or tertiary structure to an alcohol. Here you can see the spectrum of 1-hexanol and here are the peaks. You can see this is a broad peak due to OH, it is nearly 3000 and here you can see it is splitted and this is due to the sp3 carbon hydrogen stretching we have discussed in earlier slide. Here you can see this is also CH2 bending vibration and CH3 bending vibration. This is due to nearly 1000 to 1200. This is due to this phenolic group, this carbon oxygen group, carbon oxygen stretching and this is a 1-hexanol structure. OH stretching vibrations. When alcohols or phenols are determined as a pure or we can say neat liquid films is common practice, a broad OH stretching vibration will be obtained for intermolecular hydrogen bonding, that is hydrogen bond formed within different molecules and it will be observed at value 3400 to 3300. Phenols also show hydrogen bonded as the alcohol is diluted with carbon tetrachloride. A sharp peak non-hydrogen bonded appears at about 3600 to the left of the broad band spectrum. When the solution is further diluted, the broad intermolecular hydrogen band is reduced considerably, leaving as the major band and free OH stretching absorption. Intermolecular hydrogen bonding weakens the OH bond, thereby shifting the band to lower frequency or we can say lower energy. Here you can see the difference. This is hydrogen bonded OH only neat liquid A, free hydrogen bonded OH dilute solution for very dilute solution and you can see the difference. It is left to this OH, here only this broad spectrum is there when no dilution is there, when dilution is there you can see this kind of peak is also there and in very dilute solution you can see which kind of a spectrum will be there for OH stretching region in phenols. Some workers have used the position of free OH stretching band to help assign a primary, secondary or tertiary structure to an alcohol. For example, free stretching occurs nearly 3640, 3630, 3620, 3610 for primary, secondary, tertiary and respectively for phenols. These absorptions can be analyzed only if oxygen hydrogen region is expanded and carefully calibrated. Under the usual routine laboratory condition, these fine distinctions are of little use. For more useful information is obtained from carbon-oxygen stretching vibrations. Intramolecular hydrogen bonding. What is that? When hydrogen bonding present within the same molecule. Here you can see this is hydrogen when it is attached to an electronegative atom with a covalent bond, and now it has a hydrogen bond, intramolecular hydrogen bond with the electronegative atom of within from the same molecule or from the same carbon. So, this is called this is intramolecular hydrogen bonding present in orthocarbonyl substituted phenols, which usually shifts broad band to a lower frequency. For example, OH band is centered at about 3200 in neat spectrum of methyl salicylate, while OH bands from normal phenols are centered at about 3350. The intramolecular hydrogen bonded band does not change its position significantly even at high dilution because the internal bonding is not altered by change in concentration. So, you can differentiate between the types of hydrogen bonding, whether it is intermolecular or intramolecular depending upon the dilutions. Although phenols often have broader band than alcohol, it is difficult to assign a structure based on this absorption. Use the aromatic carbon double bond carbon region and the carbon oxygen stretching vibration to assign a phenolic structure. Finally, the OH stretching vibrations in carboxylic acids also occur in this region. They may be easily distinguished from alcohols and phenols by the presence of very broad band extending from 3400 to 2400 and the presence of carbonyl absorptions, which will not occur in case of alcohols or in case of phenols. Now, see carbon, oxygen, hydrogen bending vibrations. This bending vibration is coupled to which? Hydrogen, carbon, hydrogen bending vibrations to yield some weak and some broad peaks in the region of 1440 to 1220 centimeter inverse. These broad peaks are difficult to observe because they are usually located under the more strongly absorbing carbon hydrogen bending peaks at 1375. The strong carbon oxygen single bond stretching vibrations are observed in the range of 1260 to 1000. Since these absorptions are coupled with the adjacent carbon-carbon stretching vibrations, the position of these bands may be used BD assign a primary, secondary, tertiary structure to an alcohol or to determine whether a phenolic compound is present or not. This table you can see the carbon oxygen and oxygen hydrogen stretching vibrations in alcohols and in phenols. You can see the values are decreases when we are going from phenols to 3 degree, or we can say tertiary alcohols or secondary alcohols or primary alcohols, while the values of oxygen hydrogen, you can see for phenols this oxygen hydrogen stretching vibrations will occur at 3610, for 3 degree it can occur at 3620 and the values are increases when you are taking in a very these conditions. Here you can see this is a unsaturation on adjacent carbon on a cyclic structure lower the frequency of carbon oxygen absorption. So, you can see the value decreases from 1100 to 1070, and here you can see the value also decreases, and these are the more examples. These are for 2 degree and these are for 1 degree. The spectrum of 1-hexanol, a primary alcohol, has its carbon oxygen absorption at 1058, whereas that for 2-butanol, a secondary alcohol, We have seen in earlier slide, it will be carbon oxygen absorption will occur at 1109. But both alcohol have their carbon oxygen bands near the expected values. Phenol will give you carbon oxygen absorption at about 1220 because the conjugation of oxygen within the ring which shifts the band to a higher energy due to double bond character, more double bond character. In addition to this bond, oxygen hydrogen in plane bending absorption is usually found near 1360 for neat samples of phenols. And this later band is also found in alcohols as neat undiluted liquids. It usually overlaps carbon hydrogen bending vibrations for the methyl group at 1375. These carbon oxygen absorptions are shifted to lower frequencies when unsaturation is present on adjacent carbon atom or when oxygen hydrogen is attached to a ring, and it can shift from 30 value to 40 values. Now ethers, what are ethers? ROR. Ethers show at least one carbon oxygen band in the region of 1300 to 1000. Simple aliphatic ethers can be distinguished from alkanes by the presence of carbon oxygen band. In all other respects, the spectra of simple ethers look very similar to those of alkanes. When we are eliminating this carbon oxygen, it look like that it is a alkanes. Aromatic ethers, epoxides and acetals are discussed, will be discussing in coming slide. Ethers carbon oxygen, the most prominent band is that due to carbon oxygen, we have stated in this point also. Absence of this band is required to ensure that carbon oxygen stretching is not due to an ester or an alcohol. Phenyl alkyl ethers gives two strong bands at about 1250 and 1040, while aliphatic will give you bond strong at 1120. Here you can see this is the IR spectrum of anisole. Here you can see this is the percentage transmittance and this is the wave number value. It decreases from 4000 to 400. Here you can see this value is due to the sp2 carbon hydrogen stretching and this is due to sp3 carbon hydrogen stretching. These value is due to the carbon double bond carbon. Which carbon? This aromatic carbon double bond carbon. These are carbon oxygen stretching which are prominent in case of ether, and this shows monosubstitution. The infrared spectrum of dibutyl ether, that is aliphatic ether, you can say this is R, ROR, and here are the bonds, and you can see this carbon oxygen stretching will distinguish it from alkanes. Ethers and related compound such as epoxides, acetals and ketones give rise to carbon oxygen carbon stretching absorptions in the range from 1300 to 1000. Alcohols and ester also give strong carbon oxygen absorption in this region, and these latter possibilities must be eliminated by observing the absence of bands in oxygen hydrogen stretching and in carbon oxygen stretching region respectively. Ethers are generally encountered more often than epoxide, acetals and ketones. Here you can see the structures. This is ROR, or we can say dialkyl ether. Here you can see one aryl group is there, so aryl ethers. Because of this vinyl group, this is vinyl ether, this is epoxide and this is acetals. Or we can say when this H is replaced by R, this will be ketones. Now dialkyl ethers. The asymmetric carbon oxygen carbon stretching vibration leads to a single strong absorption that appears at about 1120. The symmetric stretching band about 850 is usually very weak, and the asymmetric carbon oxygen carbon absorption also occur at about 1120, a 6-membered ring containing oxygen. Aryl and vinyl ethers. Aryl alkyl ether give rise to strong peaks. For asymmetric, it will be nearly 1230. For symmetric stretching, it will be nearly 1040. We have seen the spectrum of anisole. Vinyl alkyl ethers also give two band, a strong band assigned to asymmetric stretching at about 1220 and a very weak band due to symmetric stretching at about 850. So, in this way you can analyze whether which kind of ethers are there. The shift in asymmetric stretching frequencies in aryl and vinyl ethers to values higher than were found in dialkyl ethers can be explained through resonance. For example, carbon oxygen band in vinyl alkyl ethers K shifted to a higher values because of the increased double bond character. We have already stated in earlier lecture that if there is increase in double bond, the K value will also get increased, which strengthens double bond. In dialkyl ether, the absorption occurs at 1120. Here you can say this is vinylic group, vinylic ethers, and here you can see these are the two resonating structure because of the delocalization of these pi electrons over here and this oxygen because of the electronegativity, and the value will occur at 1220 because of this delocalization. Here you can see simple alkyl ether and no resonance will occur, so value will be decreases 1120. So, here in this way you can easily analyze the distinguish ethers, whether this kind of ether will present or this kind of ether will present in a given organic compound. Epoxides. These small ring compounds give a weak ring stretching band, or we can say breathing mode in the range 1280 to 230. Of more importance of the two strong ring deformation bands, one that appear between 950 and 815 due to asymmetric and other between 880 and 750 due to symmetric vibrations. For monosubstituted epoxides, this later band, this one that is 880 and 750 will appear in the upper end of the range nearly 835. For disubstituted epoxides, the absorption will get lower down closer to 775 value. Acetals and ketals, molecules that contains ketal or acetal linkage often give 4 or 5 strong bands in the region 1200 and 1020. These bands are oftenly unresolved. Unresolved means we cannot isolate, we cannot easily identify in the spectrum these values. Now, carbonyl compounds. The carbonyl compound is present in aldehydes, we are very much aware of this fact, in ketones, in acids and its derivatives also. What are derivatives? Esters, amides, acid chlorides and anhydrides. This group absorbs strongly in the range of 1850 to 1650 because of its large dipole moment. We have already stated that the compound which are having significant dipole moment only will give you IR spectrum, otherwise will not give IR spectrum if the dipole moment, overall dipole moment of a molecule is 0. Here you can see the range. We can differentiate these carbonyl compounds, or we can say anhydride, acid chloride, acid anhydride, ester, aldehyde, ketone, carboxylic group, amide group. So, these you can see the values are similar values, nearly values from 1850 to 1650, but still we can differentiate it between these values. The range of values can be explained through the use of electron withdrawing effect, or we can say inductive effect due to electronegative nature of that particular atom, through resonance effects and through hydrogen bonding. The first two effects operate in opposite way to influence the carbonyl stretching frequency. An electronegative element, or we can say inductive effect, may tend to withdraw the electron towards itself between the carbon and oxygen atom due to electron withdrawing effect. So, the carbonyl bond, carbonyl group, or we can say carbon oxygen double bond somewhat become stronger. A higher frequency absorption will be observed in this case. Since oxygen is more electronegative, this effect dominates in an ester to raise the carbonyl frequency above that of a ketone. A resonance effect may be observed when the unpaired electrons on a nitrogen atom conjugate with the carbonyl group, resulting in increased single bond character and a lowering of carbonyl absorption frequency. This second effect is observed in an amide. Since nitrogen is an less electronegative than oxygen atom, it can easily accommodate a positive charge. The resonance structure shown introduce a single bond character into the carbonyl group and thereby lowers the absorption frequency. Here you can see this is the structure of ester RCOOR, and these are the resonating structure of amide. What is amide? RCONRR. Here you can see 2 hydrogen atoms get substituted by R groups. So, what you are looking over here, you can see because of this electron withdrawing character of this oxygen, this value get changes, and here you can see these are the resonating structure, and this resonance will affect, or we can say lowers the carbonyl frequencies. In acid chloride, the highly electronegative halogen atom strengthen the carbonyl bond through an enhanced inductive effect and shift the values to even higher than are found in esters. Anhydrides are likewise shifted to frequencies higher than are found in esters because on a concentration of electronegative oxygen atom. In addition, anhydride gives 2 absorption bands due to symmetric as well as due to asymmetric stretching vibrations. A carboxylic acid exists in monomeric form only in very dilute solution, otherwise it exists as a dimer. Here you can see this is the intramolecular hydrogen bonding in carboxylic group, and here you can see the dimer of a carboxylic group, and which strongly absorbs at about 1760 because of the electron withdrawing effect. Because of the electron withdrawing effect we have discussed in earlier slide of this carbonyl oxygen or this hydro. However, acids in concentrated solution in the free of neat liquid or in the solid state tend to dimerize via hydrogen bonding. This dimerization weakens the carbonyl bond and lowers the stretching force constant and resulting in the lowering of carbonyl frequency of saturated acids to about 1710. Here you can see the difference between this is aldehyde group because of presence of one hydrogen, and here you can see this is the ketone. Ketone absorbs a lower frequency than aldehyde because of their additional alkyl group, which is electron donating as compared to this hydrogen in case of aldehyde and supplies electrons to the carbonyl group. This electron releasing, you can see the electron releasing characteristic nature of this R group weakens the carbon oxygen bond in the ketone and lowers the force constant and the absorption frequency. So, we have discussed many functional group, we have discussed carbon, hydrogen, stretching vibrations, bending vibrations in case of alkenes, in case of alkynes, we have discussed in alcohols and phenols, in epoxides and ketones. So, you can differentiate easily the kind of functional group present in the given organic compound by the depth knowledge of IR spectroscopy. Hope you understood this lecture. Thank you so much.
Dear friends, we hope that with today's lecture you were able to understand the concept of IR spectroscopy. On that note, we would like to thank Dr. Vandana for coming here and delivering this wonderful lecture. And thank you dear friends for watching our lecture. Stay tuned and keep watching. Thank you.
Thank you.